Okay, let's take a look at how test environment lifecycle works. Inside of GitLab, we have some capabilities for managing test environments in a lifecycle managed way. Lifecycle simply means from the time something is created, updated, and then completely removed. So the entire lifecycle is managed by GitLab. Most people's experience of this in any CI is a pipeline job as an environment. A container provides a specific environment for doing things in. Anytime we encapsulate a model in the loop, software in the loop into a container, then we are in essence encapsulating an environment for that process. This capability is table stakes in CI, and most people's experience with maturing their CI and maturing their environment capability is to create jobs in CI. Interestingly, this gives us really essentially a per pipeline execution lifecycle. What that means is the resources required to accomplish a test are provisioned, used, and removed all within each time the pipeline runs. This is great and the preferred way for anything that is simple enough to do this way. So it's not a bad thing. It's just the first level of encountering how to do testing in CI. Frequently, though, lots of environments, including embedded, start to get more complicated environments that take longer to set up or have special capabilities such as feeding production data feeds. And as soon as we get into that, if we try to retain that inside the pipeline, all of a sudden pipeline runs start taking a really long time. And it also is setting up the same exact environment again and again and destroying it. So there can be a literal waste of compute and time. The next level of maturation in this journey is to have environments that live longer than simply a pipeline run. Now, the flip side of this is to use something like an internal developer portal to provision an environment, either to a person, to a team, or to a project. But one of the challenges we run into there is that the actual environment is not isolated to the work being done. So when the environment's not isolated to the work being done, then we have multiple tests from multiple different code change sets being driven onto the same environment. And that environment's capability to be properly cleansed either starts to take a long time or is suspect that there is some sort of config problem going on. And so we lose that aspect of a reset environment for the same code changes. One other aspect about this per pipeline execution lifecycle is that teardown is built in or implicit or inherent and therefore taken for granted. Whenever we run a job and the job goes away, any resources it was using or had allocated, whether it's locally or in some sort of cloud service, generally go away as well, or we consider it best practice that they do. So we automatically implement a teardown stage to the lifecycle. And as soon as we step outside of the life cycle of the pipeline, then this teardown stage not only becomes something we explicitly have to think about, it becomes one of the primary challenges to handle and a primary driver of cost sprawl if it is unhandled. So let's take a look at an alternative. In GitLab, when we create a merge request, we can run specific jobs that provision resources for use by the pipeline. But those provisioned resources can live longer than the pipeline. So we can provision virtual embedded environments from a variety of manufacturers. You would essentially use any available APIs that these organizations allow you to have to create a special job for creating and updating the environment and a special job for destroying the environment. It might be as formal as infrastructure as code, or it might simply be an API automation set that allows you to do this either in a cloud service or on local resources or within containers. Whatever the capability is, you can tap into that to create a couple special jobs. Then GitLab becomes aware that those jobs are creating and destroying an environment and adds a lot of new interesting features to the GUI as well as capabilities to GitLab. We then use our CI pipeline runs to run tests on these environments. Now, it's important to realize that we can update the environment every time the code changes if that application code is also in that environment. Then we run our tests and get that feedback into our pipeline. Just a quick note that we could potentially also add hardware environments in here if they are of such a thing that it's okay to allocate them for as long as a merge request might be alive. One of the challenges here is we no longer have the implicit teardown. So whenever we have non-lifecycle managed environments, that lack of teardown can lead to massive cost sprawl. I've worked in organizations where the creation of environments through a developer portal capability was given out to developers, but there was no natural understanding of when are you done with the environment and can we destroy it and who authorizes that. And so eventually the spend on pre-production environments was 10 times as much as what it cost to run the same set of applications in production. We want to borrow the fact that this happened in the cloud development sphere and completely solve it day one if it's solvable in embedded. There's no need to go through a 5 or 10 year life cycle where everybody realizes, oh my goodness, environment sprawls out of control. Now we need to do something about it when we've already repeated that cycle once and solved it inside of DevOps cloud realm. So one of the things that GitLab does is before it actually deletes the branch during a merge, it intelligently runs the environment destroy job, which then cleans up the environment. And you close this loop. It closes the loop technically, authorization-wise, and behavior-wise. And what do I mean by that? Well, when environments are difficult to request and deploy, developers tend to leave them sitting around rather than destroying them. But then if we auto-destroy them, you think, well, developers won't want to auto-destroy them. Well, if it's just as easy as creating a branch to create a new environment of the same type, they definitely prefer a clean environment. When everything's automated, hands-off, and sort of transparent, this allows for the behavioral issues around environments, the cost issues, and the testing assurance capability all to be working well. And so we call this per merge request lifecycle environments. So the concept is the environments have a lifecycle. And that lifecycle, instead of being per pipeline, is per merge request. It's fully managed, so it also handles the destroy. And we know that people are done with the environment when they're ready to merge their code or when they go to delete the branch because they no longer need it. Environments also have some other very interesting controls, such as timeouts. So if an environment's left running for 2 weeks, I can say, time it out, auto-destroy it. And when we auto-destroy it, it's okay because if the developer comes back and needs it, they just press the deploy job for the environment and it will be redeployed clean and ready to test with the latest code. So there's some other capabilities we inherit once we make this a part of the actual orchestration system. So that's kind of the concept of environment lifecycles, reasoning from what you're probably familiar with, which is creating testing resources with inside of a pipeline, and noting to you that that's really a life cycle because we destroy all the resources in there naturally. And then we can have this next capability that also is life cycle managed because GitLab has this as a special set of features. But also we don't tie environments to be too long running or inadvertently where they'll be used for many different code projects before they're ever cleaned up or destroyed. So that's how test environment lifecycle works inside of GitLab. Just wanted to make one quick note. We have talked about merge request lifecycle managed environments, which on this diagram is the upper left dotted square with the purple label. There are many other things you can do once you have environments as code built into your project inside of GitLab. You can do a lot of other cool environment things. I'm just going to leave it to your exploration. If you want to look at this, in the green box is the URL to watch a video that unpacks this slide slowly and explains each of these different ways in which you can use environments. It's my pleasure to show you a little bit about how GitLab can handle embedded use cases. As we go through this information, I want you to think about the fact that GitLab is a extensible platform. So some of the things you'll see are elements that I've created, such as compliance frameworks. And those compliance frameworks I've named by some common names that you might recognize. But it doesn't mean that GitLab has some magic way of waving a wand and making your software compliant with a given standard. It means that GitLab is a rich set of functionality for DevOps that you can configure to meet the requirements of compliance programs. And there'll be other aspects like that as well as we go through, and I'll try to call those out. So the first thing I want you to notice is that in this repository, we have compliance frameworks applied. Compliance frameworks are a really powerful way of grouping specific policies that you can then apply to many repositories at once. These compliance frameworks allow you to group pipeline execution policies, merge approval policies, all kinds of policies in GitLab. And when you really think about it, that means that software is under compliance requirements before there's even a repository, which means it's really as far left as we can get. So let's take a look at this particular policy. We can see here that it is specifying that we run an embedded specific scanner. And then it's also specifying no medium or high vulnerabilities allowed. So this is a kind of a policy that's trying to make sure that we do our appropriate scanning. When we click on the UNCR evidence collection, we have a policy called complete pipeline trace evidence. And so this applies some jobs that allow us to collect everything that happened in the pipeline, including what pipeline code ran, the exact version of it. So let's take a look at how this affects our project. Compliance pipelines just make some of the functionality we're looking at required of developers. So when we start digging into individual details within the merge request, I also just want to point out that compliance and the security policies that back it all live under a dashboard, which is cumulative as you go up in the hierarchy. So if we look at a vulnerability report, we can see all the vulnerabilities that were accepted into protected branches throughout our entire group hierarchy. And it's at every level. So if I have a team level, I could go to that level in GitLab and see this just for a team and all of their projects. If I want to go global, I can go to the root group of that particular organization. Another important thing is you may have a security team that's responsible for both embedded and non-embedded security. And so you can see here that we have a web project in our hierarchy that is doing GitLab standard scanning, and it's coming up with many findings itself. So we get to see a mix of these findings, or we could go down to say if an embedded group is a sublevel, we could look at that embedded group and see only the embedded findings of that embedded group. But you can see GitLab scanners working in here. And then as we go down, just see here how far we have to go. Let's show another 100 items. Okay, next. We see here Code Sonar SAST. So this is the third-party embedded specific scanning tool, and it's able to fully participate in both our merge requests as well as all the way back here to the security dashboards that anyone would use who's working with security. So that's a view of the fact that this can be a consolidated panel for those who are working with your security information. We also have a security inventory, which can give us a heads up on which repositories have tools and functionality implemented for security and which ones don't. And so these reports are all fed by the information that the security scanners that are being required are feeding up. So, all right, let's drop back to our project here. And within a project, the single source of truth for changing code is the merge request. So I'm going to go to code merge requests. A lot of organizations that do embedded are used to doing most of their build and verification activities locally. And you can still do some of this, but to the degree that developers don't share that information, it's harder to help each other or to take advantage of automated compliance and automated security workflows that actually help them by requiring as little as possible of their time to do the right thing and resolve the right problems. So something to keep in mind is that this kind of collaboration in a single source of truth for all changes requires that we start using collaborative automation so that those results can be collected and put together here in the merge request. So one of the things that policy required was that a certain scanner be run. And we'll just see how that works. When you're using policies, it inserts this job pipeline policy pre and another job pipeline policy post, or another stage, and we can put jobs in there. So my two compliance frameworks are doing 3 policies, and a couple of them are inserting some of these jobs. One of the jobs here is making sure that we have an embedded specific scanner doing our scanning. And so that embedded specific scanner emits its results in GitLab SAST JSON, which means they come right into the merge request widget for security findings. So these are third-party findings. And if we dig into here, we can see that this particular scanner is embedded specific. So it's got a lot of the MISRA C standards that you're used to looking for. So it covers code quality, not just security scanning. And importantly, it covers things that could be undefined behavior. So that might cause a hang or a crash in a machine. And so embedded specific scanners don't simply only look for security. They tend to look for things that are as impactful to embedded applications as security findings, anything that would terminate the machine. The other interesting thing is that when a scanner is well integrated, it can use the GitLab's AI capabilities, including Resolve with AI. So I previously pushed this button and GitLab created this new merge request here. And when I open this merge request, you can see that it's got a new branch about remediating this vulnerability that it wants to merge into my branch. And what we can immediately see down here, and by the way, the MR has got the full documentation that we saw in the finding record, but this pipeline is passing and there's no security vulnerabilities. So if I merge this, my branch that I'm working on for my feature would immediately become security problem free. Now, another important aspect here is that GitLab makes sure that we bring security into the developer's everyday habit loop of the merge request, but that it's not noisy. So all of these findings were introduced by code changes I've made, or some of them might be due to new findings in the wild that my code, it now surfaces the fact that, hey, did you know there's a new finding or a new CWE, and your code happens to exhibit that CWE. But that means that these findings are very relevant to my work. I'm not seeing a list of all the past findings that were accepted into the software like we saw on the dashboard. And so it's a diff. It's a security level findings diff to make sure that we don't re-report to you stuff that's already been dealt with or accepted into the protected branches. When we're inside of here, now that we have some findings here, this merge approval policy is blocking the merge request. So this rule was injected by our policy, and this rule is now requiring at least one approval from anyone in the indicated group. Interestingly, if I was to merge that MR and solve the security findings, this would immediately become optional. So it's complete workflow automation of a task that's frequently very humanly painful for folks. And one of the things that's really important to when you look at this sort of security workflow automation is to realize that by inserting it this way, you're doing away with the need to hire more people to run around with spreadsheets or emails and ask if vulnerabilities were handled. Usually they're long past the cycle where that could have been dealt with efficiently. And so now stuff's already being integrated. And so all of those manual human processes become workflow automated. Developers have an incentive to engage in their findings. They're also not stopped in CI. And being able to inject a merge approval rule means this code cannot go anywhere near production without more approvals, but we also don't fail their tests in CI. So an example would be if we have a finding in a new version of a board support package, and someone in our organization who's assigned to that duty needs to work with that upstream provider and get that fixed, or fix it for them and ask them to send a new version. Well, in the meantime, you don't want CI to be failing because it will hamper or make the developer's progress impossible. So this is a real productivity boon to have just the findings that the developer has accidentally created, have the ability to automatically assert a policy that says you can't merge it. If they are able to resolve it themselves or with collaboration, once it's resolved, then that policy becomes optional. So it can let you really scale better at DevOps automation, functional safety compliance standards you're under, or some of the new cyber physical regulations. You can be more compliant more quickly and stay efficient, not have to balloon headcount in order to accomplish that. So let's dig a little bit more into the pipeline. I'm going to dig into this pipeline and we're going to take a look at some of the other capabilities in GitLab. One thing we want to look at is the ability to use CI/CD components. And why this is important for embedded developers is that learning a CI language could be relatively distracting for them in order to get access to CI. So what you frequently want to do is find one person on the team that has a real deep interest, or maybe you're fortunate enough to have a developer productivity team that actually helps with creating CI capabilities. Because we have GitLab CI/CD components, we can create some really interesting functionality. So I'm going to show you the results of this job. Basically, it wraps something called Git version, and Git version is a really cool piece of technology that can determine your next SEM version automatically without having to store the last used version anywhere. and it's smart about branches and the number of commits on a branch, so it can increment the version numbers. This is the version number it came up for us here. Because we're in a feature branch, it is a pre-release branch, so it has text in it. But as we merge up towards the release branch, this could become a more and more standard version that we want to use. With this particular component, if you don't have a Git version YAML, it uses the most common and basic configuration. But if you add a Git version YAML, you can go crazy on how you want version numbers to work across branches and all kinds of things. So because this is wrapped in a component, for a developer to use it, I want to show you the code that's required for a developer to use this. To the right branch. And the only line of code is right here. So they include this component. It pulls in that job in the pre-stage, which publishes a version number which is collected into GitLab CI variables. So then every other job afterwards has access to the version number that has been assigned to this exact pipeline run. You can use it to version binaries, use it to version packaging, use it to update the code files themselves, if that makes sense. But this thorny problem of versions is solved that quickly. And we're going to look at the fact that a lot of the other hardware and software in the loop functionality we're creating is also solved by components, which you can see are referenced here. So this is a really important capability to reduce or eliminate cognitive load for your embedded developers who are working on customer solutions. They don't have to learn CI inside out if you can get your components from your vendors or start building some of your own internally. Another interesting thing is for CI/CD for developers, they can frequently have a challenge in that they're using CI componentry they're not fully familiar with. They're having a problem with it that looks like a bug, but at the same time, they're pretty sure that if that bug was there, everybody else would be broken. So they're wondering if they've misconfigured something, but they can't really figure out what the code is doing. So this is a place where explaining with AI can give us a lot of advantages because we can become just enough expert at just in time at something like, what does this CI job do? So I'm going to ask GitLab Duo, what does this CI job do? And all we have is the log. We're not even looking at the code. And so we could also find the code because it's easy to find for components and ask it about the code, but it's actually able to give us a super great explanation right here without even having to do that. So from the log alone, I'm able to get a very reasonable description of what this does. I actually built this component, so I know this description to be accurate as to what it is actually telling me that this code is doing. So the ability to explain with AI allows embedded developers to be able to explain the CI that they're using or explain errors, figure out if it's a compiler problem with their code or is it a problem with the CI itself, be able to disambiguate that fairly easily. So let's look at some of the embedded specific componentry in here. This first one here, Walkwe SIL. Walkwe is a small board testing platform that works with the Raspberry Pi Pico W. And this platform allows you to upload your actual firmware and run a test while monitoring the serial port from a remote service. So we're able to do what we talked about earlier as an environment as a single CI job. We upload our firmware into this cloud service, then we run the testing framework that Walkwe has, and we get that test result back. So a great example of first level software in the loop, as well as being able to have a life cycle that's within the pipeline. I want to take a step back and show you that even though the Walkwe tool doesn't output standard JUnit, I can still collect its evidence with a keyword that's called expose as. It allows me to expose arbitrary artifacts. If I wanted to spend a little more time, I could have potentially sliced that information that came out of that tool into JUnit, or if you can output JUnit, then you can get better reports. And we'll take a look at that in just a bit. All right, let's dig back down into our pipeline. So that's an example of doing something right in the loop. We also have our scanning here. Another thing that's important with embedded specific scanning is that you do abstract tree analysis instead of code smells. This is where we create an entire tree of every path through the code and then identify some important things. This is hard with C language due to the way it does compiles, and we have to watch the compile. So it's important to be able to watch that. And then when we get the data, we can find that undefined machine behavior that might be a consideration and gets raised as a finding. We then have this walkwe sil environment deploy and walkwe sil environment destroy. So if you watch the part of this video that talked about GitLab's merge request lifecycle environments, these two jobs implement it. And these two jobs also, simply the first job has a special keyword called environment that causes GitLab to be aware that this particular CI job is deploying an environment, and one that we will leave around. It's not part of the ephemeral resources of the pipeline. The destroy job is super important, and it's linked to the create job. And that's because this is what makes this lifecycle managed. We know what to do when it's time to tear down. And we can also tear down at various times. So as a developer, if I think this environment is soiled, I can hit stop, or I've got config rot, I can hit stop, and it'll destroy the environment, and then I can hit deploy again, and it'll redeploy it. So I can manually clean up the environment if I'm suspicious of it. But also we can have timeouts. So we can say this environment's been running for a week, and we destroy it. The reason why that's possible with this capability is when you're using environments as code, you never want someone to log in and snowflake the environment. If they haven't logged in and snowflaked it, it's not a problem to destroy it because we just press the create to recreate it. You don't have to do timeouts. So if there's a reason that developers would log into an environment and change it, you can not disturb it with timeouts. And then also when we do a merge delete branch, we have all the signals to know that someone is done with the work that required this environment, and they are indeed authorized to destroy it, because when they do a merge delete, they're making a destroy the environment request. That's the capability we had. Now GitLab understands that there's environments in here, and it treats them as special capabilities and objects. So we're going to open up the environments tab. So that's basically operate environments. And here we can see a bunch of environments associated with this project. I'm going to open one of these environments, and we're going to look at basically the ability to do human in the loop, which means that I'm going to be able to interact with the environment graphically. However, that is not a requirement of these type of environments. They could be set up completely just for another CI job to run some sort of test or scan on them. So when I show you that they have human in the loop capabilities, this is an additional capability to also just supporting purely automated environments that use with automation. So I'm going to open this environment. It loads into walkwe again, into a more graphical environment. It has my source code on the left and my depiction of my device on the right. And when I hit play, I get to interact with this device as much as we can. We can see it blinking. If I went back to my branch and changed this milliseconds to 5,000, the next time I opened the environment, this would be 5,000, and I could press play and test that. So that's the example. There's very complicated environment providers out there that you can benefit from having these longer lifecycle environments. MathWorks has all kinds of virtualization environments for testing embedded, both testing the actual data models as well as testing emulated hardware. And then we have Synopsys with VCS, which allows you multi-device interconnected testing with production-like data feeds into the whole model. So all of these virtualized systems, you can pull them in and provision them during a merge request and have them deprovisioned afterwards. So that's the concept of merge request lifecycle environments and why it can be important for embedded. And they are production-like environments. We could also deploy a developer environment this way, and you go in and actually use the tools in there. It's just that you tend to want to make sure that this capability supports true production level environments as well, where there's expected to be no logging in by anyone. Another thing I want to show you is hardware in the loop. So this is a child pipeline that's doing hardware in the loop for us. The child pipeline allocates the hardware, then runs the child pipeline, and then deallocates. So it's very much got the concept of orchestrating shared hardware that's hooked up to GitLab runners so that we can orchestrate it. It's also capable of pipeline locking. And what this does is, first of all, it makes sure that anyone who's not using the hardware in the loop component is not able to use this runner no matter what. But the second thing it does is it makes sure that when you run multiple jobs, that they all stay on the same hardware and with no interruptions by anyone else. So that's very important when you're going to flash the device in one job and then run a test in another job. We can see here that we flashed the device, and I have actual a little 3-device cloud by my desk that this runs on. So we can go back here and find out exactly what runner it ran on. And we can see that it's auditing that the pipeline that we are running out of as a requested job is the same as the pipeline assigned to the device. So that information is evident, and it looks here like we had a successful flash. Then I used Robot Framework because it's fairly common, but whatever your testing framework is, you do your test framework job inside of this same pipeline, and then it gets allocated to the same runner. You can see that I've had some failures here. Robot can output JUnit XML, which is something that GitLab can consume and visualize. So we're going to take a look at that here in the merge request. So that flows up into this particular report. So we have the visualizations of the report. We can view the details of what failed. It's also possible to collect the JUnit as an actual text artifact, which we've done here. So occasionally JUnit output has some very rich HTML reporting functionality that you might want to visualize directly. And so I've got it both ways here, visualized as a GitLab visualization, as well as I could window through to the actual artifact and look at if they've got some additional interesting reporting functionality in their output. So that's the aspect of hardware in the loop. And in this case, GitLab is the only software involved in coordinating an on-premise device cloud. And essentially, you would run GitLab Runner on a compute device that is attached to the embedded setup. The important aspect about that is that whatever you can do with the developer's workstation to an embedded device, you can do with the on-premise device cloud. The other thing to keep in mind is that we can make sure that that shared hardware is not being bottlenecked or unused at certain times of day or the week. You can queue up a lot of builds that then can process on the hardware, and developers have a better time of using hardware. They don't have to schedule it manually, which causes a lot of downtime for the hardware where it's not being used, low utilization. And also, they don't have to worry about having to come in early or on the weekends in order to get hardware access. So this can be a real time saver for embedded developers. The last thing I want to show you is we enabled a policy for UNCRA, and that policy is enforcing a pipeline jobs to collect a comprehensive evidence of this pipeline run. So here it's turning on SALSA manifests so that they are turned on for any job that collects artifacts. But then importantly down here, this job iterates through everything in our pipeline, and it goes and gathers the exact code that was used in the pipeline. It gathers all SALSA attestation manifests that are in the pipeline. It gathers all artifacts of all types. It gathers all the job logs. And then it puts them in a zip file and signs it, in this case using the built-in signing of GitLab. And then once it signs it, it repackages it into another archive with the signature and the original archive. And then you can export that as a GitLab package. If for some reason you want to make it public, you can export it as a release. And then also, because it's a self-contained archive, if you have another system of record where it's very important to have all that information, you can export it to there. By capturing both types of the CI YAML file as well as the logs, we get very detailed information like what exact container SHA was used to process and build this software. It's traceability both for the purpose of compliance, but also build reproducibility, which is also very substantially important in embedded. So that's a walkthrough of some of the really rich functionality we have in GitLab. You might have questions like, well, can I do X or can I do Y? And what I'm trying to show here is that through GitLab, with the magic of components, there's a lot of things you can do and expose to your developers in an easy way. If we go ahead and look at this particular file here, we see that we're using a component for the device cloud. So that eases the device cloud. We're using a component for our compiler. and then a component for code sonar, which ends up combining with the compiler component. And then we're using a component for the single job for the software in the loop, as well as the software in the loop environment. So these all end up adding different jobs to my actual CI. In fact, I don't see them here. I actually have to go to full configuration here. And this full configuration is what the compliance section was actually downloading so that we have the exact code that ran to generate these exact artifacts. That's another aspect of all of this is implementing as components eases developers' cognitive load for CI when they're really needing to focus on their embedded use case. So that's everything I have to show you in this demo. I'm really hopeful that you understand and see the immense value of not only the technical features of GitLab to service your needs, but also this aspect of bringing things up to the MR level and being able to apply policies that start to automate some processes that are very error prone in most organizations. If you think about where you need to go in the next 2 to 3 years with some of the cyber physical regulations like UNCRA, UN 155, and US Cyber Trust Mark, those are important. You also have your legacy compliance like functional safety 26262 for automotive, DO 178C for aerospace. All of these compliance regimens benefit from being able to collect the full pipeline evidence and being able to enforce policies that prevent new vulnerabilities from entering the software inside the developer's everyday habit loop. Thanks for your time.